We're currently on like 50 participants, which is awesome. Yeah, we're about T-minus 3 minutes. Right, now before we start, I'm going to put a disclaimer out there, okay? I'm really bad with pronunciation of names. So if I butcher your name when you've sent me a message on the chat, I apologize beforehand. I promise I don't do this on purpose, all right? So we are going to have some fun today and we're going to try and learn, okay? And if I say something and it doesn't make sense, or if you get lost or anything like that, then you can tell me. All right, guys, we are live. Welcome to all the grade 10 physical sciences students. I see about 50, 60 of us in here. I want to say welcome to everybody for your first session with me. We are going to be here every single day at 3 o'clock, and every single session is going to be on YouTube as well as Facebook. And the slides that I use are going to be on Google Drive, which you will be able to access. The links will be on Facebook. All right, today we are going to start with chemistry. Oh, man. Reese asked me even Saturdays and Sundays. No, I need a couple of days to prepare everything to make sure that the slides are neat and tidy and that they're fun and that the lessons are fun too. So I use my Saturdays and Sundays to prepare. So Monday through to Friday, we are here all at 3 o'clock. All right. And guys, you might every now and again see a person running through the background. I'm aware of him. He is my husband. That's okay. He's allowed to be there. And if you hear dogs in the background, I have 5 of them. So I apologize. Let's get going. So today, the big thing is going to be for you to understand this periodic table. Oi, man, I hate that thing. But why? But why? But why? But why? You always get a periodic table. It will always be in your information page every single paper you write. So the best thing you can do for yourself is to figure out how to use this periodic table effectively. And you're going to see today and this week and next week that if you don't know how to use your periodic table, you're going to be very, very lost. Okay, guys, your periodic table is the best, coolest crib note you will ever get. All right. Now, some of you might have worked with the stuff we're going to do today, and some of you might not have. Some of you might have already mastered the periodic table, and some of you might not have. So, at our stage, I'm going to ask for a vote in here, and you guys need to tell me exactly what I need to prepare for tomorrow. But let's get going first. The periodic table is a whole table, and it has got all the chemical elements that we know of. I think it was 2 or 3 years ago, we added a few more, but it stayed pretty stock standard for the last couple of years. Now, I can see all of you guys going, oh, hundreds of years. No, not hundreds of years. We're talking like 50, 60 years. Okay, the periodic table is a pretty new idea built on ideas and inventions and experiments of the guys of old. Okay. Now, the elements on the periodic table are arranged according to a few things. We look at their atomic numbers, we look at their electron configurations, and we look at their chemical properties. Okay, now this standard modern periodic table is organized into a grid. The rows are called periods and the columns are called groups. And if you know how to use these groups and periods, you will never, ever, 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 ever be lost in chemistry, ever. And if you're going to take physical sciences all the way through to matric, guys, chemistry is half of your mark. So, this is where you have some input. I need you guys to, in the chat, be very open and honest. No one's going to judge you here. I need you to tell me whether or not tomorrow, I need to revise the periodic table and how it works. I need for you to be very open and honest with yourself. Can you use the periodic table to write compounds, to be able to do later an SP notation, okay? And to be able to understand how electron transfer works when we're dealing with chemical bonds. Now, guys, all of those things are so easy if you can use a periodic table. I'm not going to go through the periodic table today, okay? But if there are enough of you that say, ma'am, look, please explain it, then do so, okay? And then I'll run through it. And I promise you, I will explain it to you in a way you're going to remember, all right? I like to make fun little stories about things. I also struggle to remember this stuff, okay? I'm not Einstein. I'm very average human, just like the rest of you, okay? And I struggle to understand the periodic table. I was very lucky. I had a really, really cool teacher that made all these stories and made it easy for me to understand. Okay, now I see a few of you going anions and cations, electron transfer. Okay, so what we're going to do tomorrow, okay, and I'm warning you beforehand, so that if you know how this periodic table works up pat, that I don't bore you tomorrow. Okay, so tomorrow we are going to do the periodic table revision. Okay, I'm not so much worried about the history of it. Okay, I love the history of it. I love to understand how all these people figured these things out when, you know, we didn't even have electricity. Yeah, think about that, no? But I am more interested, and it is more important for me to have you understand exactly how the periodic table fits together and how it works. Because if you understand that, then there is very, very, very little in chemistry, grade 10, 11, and 12, that can confuse you. All right. So if I look at it, there's a whole thing here on, yes, we need to especially look at electron transfer. I had a question about waves, sound, and light. Okay. What we will do is I will go and have a look at the framework that we've received from the Department of Basic Education, and I will see if I can add in a revision for waves and sound. I'm not promising, okay, but I will try. And what we'll do then is we'll post it on Facebook so that you guys know. So now that I have an idea of where you guys are, I can better go and plan how we're going to do the lessons going forward. All right, Jason, we're currently busy with chemistry, paper 2. Reese, today's lesson is going to be focused very specifically on how we represent atoms and elements, or compounds, which are molecules and ions. In the curriculum, this section is quite quick. We don't spend a lot of time on it. What we spend more time in this term on is the ability to balance equations, write formulas, and understand why it is important for us to balance equations. Okay. Do we have science every day at 3? Yes, we do. Every weekday at 3. Okay. We are not quite sure what Friday and next week Monday is going to be because it is an Easter weekend. Okay. And I know that many of you could be religious. I can't see your faces. I don't know you. Okay. I'm quite happy to teach on those days, but we also have to keep everybody in mind. When will we do physics? We're going to do the section on chemistry first, and then we are going to carry on with physics. Michaela, I hope I pronounced your name correctly. Atomic mass and diameter, that's all coming up, I promise. Okay, so let's start with what I have planned for you guys today. Now, the good news is we can manage today without you knowing exactly how the periodic table works. I kind of thought, hang on a second, maybe not, let's just see. Okay, so today's work, we are going to look at how we represent atoms and molecules. Okay, now this might be revision for some, this might not be revision for everyone. Very important. All matter is made up of atoms. And this idea is not new, guys. This idea comes from like 300 years before Christ was born. Democritus and Socrates and all of these Greek philosophers already came up with this idea that all matter is made up of atoms. The idea of atoms was very, very different to what we know atoms to be today. But that idea that all matter is made up of a really, 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 really tiny little particle that we can't see comes back from thousands of years ago. All right, now, an element is made up of only one kind of atom. So that means that all the, oh, my dad needs the internet meeting for, yes, we will end exactly at 1:45. Okay, all lessons I plan to be roughly about 45 minutes because the admin also has to take over this meeting for the next one. All right, here we go. An element is made up of only one kind of atom. That means that all the atoms of a hydrogen element looks exactly the same. All the elements in an oxygen, all the atoms in an oxygen molecule, in an oxygen, looks exactly the same. But the atoms of hydrogen look different from the atoms of oxygen. Will we be doing activities on the work we go through? Yes, I haven't got any activities planned for today because I wasn't quite sure where we were, but I will give you guys activities. They will also be in the Google Drive, which you can access via Facebook. What makes atoms different from element to element? Very specifically, very, very, very good question, Tristan. Okay, the number of protons in every atom. If an atom has one proton, it's hydrogen. Doesn't matter how many neutrons it has, doesn't matter how many electrons it has. If an atom has one proton, it is hydrogen. Done. The protons give each atom its chemical properties. So that means if I add protons, I change the element. Okay. Protons and neutrons make up mass. So yes, the mass is largely controlled by the number of protons, but it is also influenced by the number of neutrons, and we'll get there. Right, now if elements are represented on the periodic table, okay? In nature, some elements, some, not all, some elements we find as single atoms. Now they are helium, neon, argon, krypton, and xenon. Wonder what's the same about all those atoms. I wonder where I find them on the periodic table. For those of you who have an idea of your periodic table, you will have noticed that those are the atoms of the noble gases. Well done, Luke, you got there. Well done, Adrian. The noble gases, and we'll get to this later, have 8 electrons. They're stable, they're chill. They don't have to make friends with anyone. They are like serious introverts. They can just be all by themselves, okay? And so they can be single atoms in nature, and they are super stable. That is why we can use them in light bulbs. When we add energy, they only give us light. They don't react, they don't go crazy, okay? They only give us light. We take the energy away and they go, okay. They come stable in nature. Why? Because they have 8 electrons. And this is the amazing thing about the periodic table. I cannot stress it enough, okay? Once you understand, and I promise I will do this in detail tomorrow. Once you understand why each element is where it is, you will understand why they react the way they do. Alyssa, sal daar klasse in Afrikaans wees? For the rest of us, will there be classes in Afrikaans? Unfortunately, our timetable is so jam-packed. All right. So we don't have time for classes in Afrikaans. Now, the only thing that is different from Afrikaans and English is some of the exact terminology. Okay. The concepts are exactly the same, right? The science doesn't change. It's simply the words. So for example, if I talk about sodium, you need to know that in Afrikaans is that natrium. All right. So guys, we're not going to do classes in Afrikaans. They're going to be in English, but the content is the same. All right. So we've dealt with the noble gases. Now I want to tell you about 7 very cool elements. In nature, some elements always are found as diatomic gases. This means that it's one hydrogen and another hydrogen, and they link like that. Okay? This is how they are the most stable. And there are 7 of them. Okay? And I will show you tomorrow how beautifully they are organized on the periodic table. It is impossible not to know them. Okay. Yes, most of these are in group 7. You are quite right. Lene, if you don't understand something in English, can I translate? I will try my best. So I will then send you a message. All right. Now, you will have noticed that these are all correct non-metals. Okay. But not all non-metals form diatomic gases. Okay, someone wanted to know if there's another platform to access the work. We are on Facebook, Twitter, Instagram, and YouTube. Okay, as soon as I know that the Google Drive is perfectly set up, I will also send the link so that you can access the files on here. Okay, but firstly I need to know that it is perfectly set up. Why is it diatomic? Dude, again, periodic table. If you think about hydrogen, one electron, it wants a friend. And so in nature, 2 hydrogen atoms like each other. They're cool, they're happy, they know each other, they're the same type, and then they bond. Can diatomic elements be found in other phases? Yes, but you have to put them under very specific conditions. Okay, so in nature, at room temperature, these 7 elements, hydrogen, nitrogen, oxygen, I haven't got it in front of me, fluorine, chlorine, bromide, and iodine. Okay, these 7 in nature is found as diatomic gases, lithium not. Now you'll notice, Tristan was asking about lithium. You'll notice that there are a ton of elements on here that I didn't, or a ton of elements on the periodic table that I didn't mention here. Okay, those guys are always found as compounds. Am I using a textbook? Yes, I like the Oxford textbook. Okay, but any grade 10 textbook follow the same order because that is what was prescribed by the Department of Education. All right. And so you can follow in any textbook. All right, guys. So quick overview of atoms. Now, atoms from different elements can combine and form compounds. Okay. Now, you'll notice that some teachers use the word molecules here. And you need to be careful not to use the word molecule when you mean compound. Sandra asked me which page is in her textbook. Let me grab it. All right, so the work we're currently doing is on page 108 of the Oxford textbook. All right, compounds form, atoms form compounds. Now, the atoms of each compound will always be in the same ratio. I'm using water here as an example. Water, you guys should all know, H2O. That means that water has 2 hydrogen atoms and 1 oxygen atom for every 1 molecule of water. Now, please don't think that this 2-to-1 ratio is true for all molecules, right? It's not. I'm using water as an example because I know that you guys know that water is H2O. It's like one of those universal things that we all know. Okay, dihydrogen monoxide. Yeah, you could call it that if you want to. Right. Now, very important, there are 3 types of compounds, and that is what you guys have already touched on in term 1, but which we are going to delve a little deeper in term 2. They are molecular compounds, okay? Molecular compounds when 2 or more atoms bond covalently. Ionic compounds, so when I have ions, this is normally when I have a metal and a non-metal. And metallic compounds, so metals. All right. Have no fear of ice cold beer. Lene, you are a trooper. I love that one. I absolutely love that one. So guys, Lene came up with a really cool mnemonic for the diatomic gases. Have no fear of ice cold beer. Vincent, did you say it earlier? Oh my goodness. I'm very, very sorry. You guys are going so fast in this chat that I'm not always keeping up. So I apologize. Okay, so we'll give Vincent the Smarties for this one. Deal? Okay, cool. So we have our 3 types of compounds. Today, we are going to look mostly at molecular compounds. All right. So when we represent elements and compounds, we can use very many different ways to represent them. Now, the thing we're going to focus on this term is chemical formula. And yes, I know there's an E at the end. Chemical formula without the E is singular. Formulae with the E is plural. And we use these chemical formulas so that we only have to use the symbols of each chemical, and we can show the proportions of each atom present in that compound. Now we have a few different types of chemical formula. We have an empirical formula, a molecular formula, and my personal favorite, the structural formula. Okay. Let's start with the empirical formula. Oh my goodness, ma'am, definition for exam purposes. Guys, when we ask you to learn a definition, it is so that you can apply to a question. Okay, I know you guys hate definitions, but I'm going to point out that that is 30% of your final mark. 30% of any question paper is definitions. So if you want to ask me, Vincent, why do you need to know them? Because they count marks. Okay? Now, guys, seriously though, if you know the definition of each thing, it is much easier for you to be able to use, for example, the empirical formula. If you don't know exactly what the empirical formula is defined as, then there's absolutely no way that you can use them. Jade, online classes, same time every day, Monday to Friday. Yes. Okay, so empirical formula. We go. It shows the simplest ratio. Someone asked me to go back to the previous slide. I will do so. There we go. Empirical formula is die empirische vergelyking. The molecular formula is die molekulêre, dink ek, formule. And structural formula is die struktuurformule. And I promise for those of you who are not Afrikaans speaking in the group, okay, the only thing I'm doing is translating, I promise. And you can see that I teach in English because my Afrikaans words for them are a bit shoddy. Someone wanted to know, what is the example of an empirical formula for H2O? Now I'm getting to that point. That's a really, really good question. So just hold on to it just for a second. Okay, we're going to move on. Okay, so empirical formula. But now the problem is that an empirical formula often doesn't tell you a lot. Okay, because some compounds actually have the same empirical formula. And then they are vastly different compounds. Okay. But some compounds have the same molecular formula and empirical formula. H2O is one of them. Okay, H2O is its simplest ratio. For every one oxygen, there are 2 hydrogens. And that is the molecular formula. When we find water in nature, okay, and I get it back down to just one molecule, then one molecule of water has 1 atom of oxygen and 2 atoms of hydrogen. Empirical formula, why diamonds and Koolstof are the same thing, very, very close. We're actually getting to diamonds and graphite today. Just hold the thought. We're getting there. Okay, so this is empirical formula. Next, we're going to look at the molecular formula. And the empirical formula and the molecular formula are sort of related. Okay, in a different session, I will show you how to go from the one to the other. However, that is not for grade 10 purposes. Okay. Right. So, molecular formula. Again, sorry. It is a chemical formula that shows you the actual number and type in a compound. Do you guys want me to show you an example of how this works in real life? Yes, okay, thought so. Hang on, give me a second. Don't panic, don't panic. Okay, so just a moment. Right. Sorry guys, I need to just move all my windows away so that I can actually access my pen. Here we go. Right. Now, in matric, you are going to deal with organic chemistry. Okay? Don't panic. Don't panic. Organic chemistry is cool, guys. It's like awesome. Right. And you are going to have a molecule called methane. All right. And methane has a molecular formula of CH4. Cool. Yes, it is a smelly thing, but it's also a really cool gas. All right. You are also going to have a gas called butane. Ooh. You guys should know what butane is. When we had so many blackouts and your parents wanted to cook, you had either butane or propane tanks and you cooked on a gas stove. And butane, I will go back to the empirical formula. Okay, methane is a greenhouse gas. Yes, not wrong. So butane, the molecular formula. Give me a second. Times 2 is 8 is 10. Okay, so now methane, if I look at the molecular formula on the side and I have the empirical formula on the side. Okay, methane has a molecular formula of CH4. If I simplify that quite far, it will also have an empirical formula of CH4. Okay, that is the simplest ratio. It is 1 to 4. But now butane in its molecular formula is 4 to 10. And the empirical formula, the definition, is the simplest ratio. This is not the simplest ratio. Both of these are divisible by 2. So if I want to write the empirical formula of butane, I would write C2H5. Yes, 2 to 5. Good job, guys. Okay, so can you see how some molecules have the same molecular formula and empirical formula, while other, normally larger molecules have different? This exam question, you are not required in grade 10 to be able to go from the one to the other. That is grade 11 work. Okay, so they give you the empirical formula, then they give you the molecular mass, and then they ask you to work backwards. But that is a grade 11 question. That is not a grade 10 question. So for now, if you make sure you know the definition of molecular formula, so it is the actual number of atoms, and the empirical formula, which is the simplest ratio of the atoms in that molecule, you will be fine. I just wanted you guys to see how this effectively works, because I know this is a bit of a weird concept. It's like, well, H2O is H2O. But especially when I'm working with organic molecules, which is grade 12 work, this compound, this thing happens a lot, where the molecular formula and the empirical formula is very, very different. Okay, so we are going to go back to the slides. Again, don't panic. And then I was asked to just go back from the slides and just go back to empirical formula. I'm going to leave this up here for a moment so that I can move all my windows back around again. And I've lost my chat. I'll just pull it back up. No. Aha, there we go. EF default formula in exam based on a question. Like I said, guys, in grade 10 level, they don't really ask this beyond asking you the definitions, okay? In grade 11, you have to be able to go from empirical formula to molecular formula, or you need to be able to go from a molecular formula back to an empirical formula. Okay. Right, guys, I'm going to move on. Ready? Here we go. So molecular formula. In some cases, it is the same as the empirical formula. The bigger they get, the more different they are. Okay. All right, guys. Now my personal favorite, okay, is structural formula. And the structural formula shows us the actual how this molecule looks. Like The actual, this is that molecule, okay? And that's why I love it, because you can get so many things from that. Back to the previous slide. Guys, what I'll also do for you from the slides is I'm busy creating a worksheet. All right, now in the worksheet, the first part of the worksheet will be the content of the slides, exactly as it is typed here, but just in black and white, okay? And obviously it will be a smaller document so that it's easier to download for you. But the PowerPoints will also be on the Google Drive. So it will be a PowerPoint as well as the worksheets. And the work in the worksheets is exactly the same as in the PowerPoint, okay? But it depends on what you prefer to do. Definition in textbook says molecule, not in compound for molecular formula. Let me have a look. Okay, guys, that word molecule you have to be so careful of, okay? Because sodium chloride, table salt, NaCl, that is not a molecule. That is a compound. It is an ionic compound, okay? And when you get to grade 12 level, they can nitpick about whether or not you use the word molecule or ion or compound, okay? So for grade 10, you don't have to use the word compound in this definition, okay? You get away with using the word molecule. But it is my firm belief that if you teach yourself to be nitpicky about words in grade 10, then it's easier to be nitpicky about them in grade 11, and even easier to be nitpicky about them in grade 12. And the reason you have to be nitpicky about them in grade 12 is because that is how it is marked. All right. It is often the difference between 50% and 65%. Or the difference between getting 75% or getting 80%. Okay. And all of that depends on what you want to achieve. All right. I'm going to go to the next slide. If I can get the mouse working here. Fantastic. There we go. So a structural formula shows the arrangements between atoms and the bonds between them. Okay. And that is why I absolutely love structural formula. Okay. It tells you exactly what that thing looks like at a molecular level. So you don't have to worry like, oh goodness, is this polar? Is this non-polar? Is it an ion? Page in the textbook. We are in the Oxford textbook. It's my absolute favorite. I really, really enjoy the authors. I'm not saying that any of the other textbooks are wrong. Please don't quote me on that. Okay. I know the author of the Oxford textbook. She's a brilliant teacher, and I really enjoy how it is written. So I use the Oxford textbook, and we started today on a roughly about page 108. I'm not exactly sure where this is. Is there a ebook version of it? I'm not sure. I would have to go and check. Bianca wants to know if we use the same code. No. Every day there are new codes. So these codes are put on Facebook. I don't know if they're on Twitter. You'll have to go and double check. And I know I send them to my learners. So if your teacher sent you today's code, then obviously she got it somewhere. So ask her or him to send you the codes again for tomorrow. The schedule for this whole week will be the same. Okay. The Facebook account, it is on Africa Teen Geeks. I'll leave those details at the end for you. Cool. Promise. Okay. Everybody got this. Now we get to the stuff. All right. But it is important to understand how molecules and these big molecules form. So let's have a look and let's struggle through it together. We got this. Okay. Now, important. Before we start working with a model, we have to kind of decide and understand how models work. All right. And you need to understand that models in science are not absolute. Okay. Just because someone has created a model and said, this is kind of what I think it's going to look like, does not mean that that is absolute. it does not mean that that is the only way ever. All right. Newton's laws have been proven to be incorrect at speeds approaching the speed of light. Okay. Einstein came up with that. Cool. But what we teach you is what we know to be true at this point in time. Okay. So I want you guys to just remember that when I use a model, it doesn't mean that this is the only truth and the absolute truth, okay? It means this is kind of what I think should be happening, okay? Now, in chemistry, why do we use models? Because atoms are that small, okay? They're so small that we can't even see them on a microscope. Cool? So we need some way for us to kind of have an idea of what this looks like. Because I know you guys, you are visual creatures. Okay, that's why you prefer to be on YouTube and Instagram than on Facebook. And Twitter, like, yeah, okay? Why you guys enjoy TikTok and Snapchat at the moment? Not my platforms. I'm sorry, you guys are on your own, okay? So in chemistry, we use models to try and show us on a way that we can see it, what is going to happen. Okay, but I don't want you guys to feel like any model I give you is the only model. All right. Mouse is frozen again. Okay, so now, why do I put so much emphasis on this? Because models show us electron transfer. They show us where the electrons are being transferred or where the two atoms are sharing those electrons. They show us what that molecule could maybe possibly look like, okay? And they give us an idea of how that molecule is going to react in certain situations. The boiling point, melting point, vapor pressure. It explains why metals you can shape without breaking them. It explains why sulfur, you have a stick of sulfur and you whack it, it's going to break, it's not going to bend. Okay. All of these things are why we use models, because it kind of makes it easier for us to understand these little nitty-gritty freaking things that we can't see. All right. Now, I'm not going to carry on from here. We have about 7 minutes left. Okay, so what I'm going to do is I'm going to show you guys the hashtags, and my dogs definitely look like they're about ready to howl at the neighbors. So apologies, guys. I'll mute my mic if I have to. Okay, so give me a second. Okay. We are not going to start with covalent structures today, okay? Because there's only 5 minutes left, and I don't want to leave you guys with half something, okay? So I'm going to quickly go through. Don't worry, I will give this all to you. Don't panic. Don't panic. Yes, I know there's a lot of it. Don't panic. All right. Now, these are the social media hashtags. We're using hashtag lockdowneschool, or one word. And if you enjoyed your experience, if you have questions, if you have comments, okay, use these hashtags. All right. Now, why is everybody panicking? Guys, don't panic. Don't panic, okay? I have been a teacher for over 10 years. Those of you who are rugby fans, there's a few of you in here, I'm sure, if I look at the names and the conversations that are going, I have taught Springbok rugby players, Springbok rugby players, and they have passed physical sciences. So do not panic, okay? Do not panic. I promise you, my job here is to break it down for you, okay? To give you the notes, to take out from all the paragraphs that you could be reading at the moment, the stuff that is important, okay? And to make sure that this time that you're spending at home, that you're getting bored, is used productively. And sometimes it's really cool to have someone else teach you, okay? Sometimes you prefer your own teacher, and that I get, okay? I'm not trying to replace your teachers in your class. I'm simply trying to make you excited, specifically about chemistry, because this is like my thing. Physics I can do, but chemistry, oh my goodness, I love it, okay? And don't panic about the fact that there's a lot of work, okay? There's always going to be a lot of work. Allow me to break it down for you, all right? So, also want to say a huge shout out, very, very big thank you to Cecil. Cecil is very kindly sponsoring infrastructure for us, and they're helping the teachers out, etc., etc. Okay, so I'm very, very thankful to Cecil. And then I also want to say free fuel. No, we're not going anywhere, dude. This is my house. Like, that's my background. This is me. Okay. But they are helping with infrastructure, and they're helping us with our data, etc., etc. Okay, so we are very, very grateful to Cecil. Then I also want to say a huge thank you to African Teen Geeks. They came up with this plan, and we have lecturers at Wits University and very many teachers all over the country who's busy adding to it. So yeah, this is really, really cool. Then the Department of Basic Education and a company called Miss Zora. I really think you guys should check it out. It's to empower women in science and technology, engineering and maths. Okay, so in terms of social media, okay, we are on Facebook, Instagram, Twitter, and YouTube. And you can go and search for Africa Teen Geeks. Okay, you can search for Lockdown eSchool 2, but on social media, on those 4 platforms, if you type in Africa Teen Geeks, you will get our pages. Okay, Vincent, they are virtual smarties. Okay, my own learners have been getting virtual smarties for 2 weeks, and I think my account at Smartyland is busy piling up. Okay, so before we go, tomorrow, I'm going to go back to the periodic table. Okay, guys? I'm going to go and make sure that you understand how to flip and use the thing. And in such a way that it's easy. Because, guys, ultimately, I know science feels like it's content and black and white on this flipping board. But it's actually really cool. It actually explains why the rain is falling and why the trees are green and why I'm sitting on a chair and not floating up into the sky. All of these things. Okay, so tomorrow, 3 o'clock, same place. Okay, not the same login. Please make sure you get your logins. Okay, either on Facebook or ask your teachers wherever you got the logins today, and invite your friends, guys. The more the merrier. And this pretty face, is what will be seeing you tomorrow. I hope you have a safe day, and I hope you learned something. Bye.